problem 2 from the AP packet. Megan? An ideal gas is initially a pressure P naught, V naught, at absolute temperature T naught, right? So it's like P naught, V naught, T naught, right? Okay. And then here is our original pressure. Here is our original volume. Here's twice the original volume. And then they helpfully give us 3 times the original volume. Here's our original pressure. Here's our twice our pressure, right? And it says that it's originally at the original pressure, right? And temperature and volume, yes? And it says it's heated at a constant volume until it doubles its pressure. Now, what do we have to do? What do we have to do to the temperature to double the pressure? We have to increase it, and specifically we need to double it, right? Yes, if we double the temperature, like if it's 100 kelvins, then up there this is 200 kelvins, right? So ultimately one of the things they want us to do is label the vertices with what the temperature is. This guy is T naught. This guy has to be 2 T naught, right? And then it says it's heated at a constant pressure until you've tripled the volume, right? So it's like, there we go. Okay. Well, what do we do if you triple the volume? What do you have to do to the temperature? This is, say, we went from 100 kelvins to 200. To triple the volume and keep everything else the same, you've tripled the temperature, haven't you? So if this is 2 T naught, triple 2 T naught, that's kind of hard to say. It's 6 T naught, right? Right? You've multiplied by 3, right? Then it says it's cooled at a constant volume until it gets down to this pressure. So that we don't move the piston, we just cool it. Cool it. Okay? Well, if you cut the pressure in half, what do you do to the temperature? Cut the temperature in half, right? So if it's 6 T naught, this is 3 T naught, right? And then it's cooled at a constant pressure until it reaches this guy here, right? So the first thing it says is it says draw the PV diagram. You'll do this on your little skill set. Representing a series of processes, only we'll give you numbers, you know. Label each endpoint with the appropriate temperature, and we've done that, right? And then it says, for this series of processes, determine the following in terms of P naught and V naught, right? The net work done by the gas, well, that's the area inside of this. It's going to be positive, and the dimensions of this are that it's P naught this way, right? That being the difference between P naught and 2 P naught, right? And it is 2 V naught this way, right? Isn't it? Right, so the net work is 2 P naught V naught, right? It's just this thing times this thing is that area. Then it says the net change in internal energy. Net change in internal energy is like from here all the way around to here. What's the change in temperature? Yeah, we start out at T naught, we end up at T naught, right? Okay. The net heat absorbed. Well, now we've got like this logic problem, right? We can do it one of 2 ways. We can resort to a formula, or we can just think about it, right? If it does this much work, right? If that equals the work, okay, and the internal energy store of this gas doesn't change, then how much heat had to flow in so that it's break even? If you go to the mall and spend $10, and I give you an amount of money so that you have the original amount of money you had before you went to the mall, how much should I have to give you? $10. There we go. We understand that, right? Okay. So what is the amount of heat that has to flow in? Yeah, it's that. It's 2 P naught, right? It's 2 P naught V naught. Now it's like, okay, let's look at the formula. What is the formula? It's work. Now what is it? Q. It's Q equals delta U plus work. Is that right? Is that our formula? Yeah, I really don't like this formula terribly much, but there it is, right? And so they're saying that the internal energy change is 0, and so this is really pretty hard, okay? If this work is 2 P naught V naught, then what does this have to be so that it's equal? Remember to subtract the, no, it's just 2 P naught V naught, yeah, there we go. I was trying to make it harder than, there we go. The net heat absorbed, and then it, optional, given that CP is blah, blah, blah. That's kind of interesting. If you look at this, there's specific heat, right? So apparently, and we don't teach this, but AP must teach this. If you want to figure out number C, here's the clues that I'll give you, is that for a constant pressure process, the heat that flows in is N C delta T, where N is the moles, C is the specific heat of the gas in terms of joules per mole degrees Celsius, and apparently they're all the same, right? If it's a constant pressure process, then you use 5/2 R, as in R, as in like the ideal gas law of R, 8.31 for us, right? And then if it's constant volume, they're saying use 3/2. And I used to teach this, and I used to remember why it was 3/2 and all this stuff, but I don't remember that anymore, yeah. But you can figure out the heat that flows in. Are we good? Are we, yeah. Yeah, really fast?
Not really fast.
Like Sound of Music in 2 minutes?
No. Nothing like that.
Okay.